And welcome to 14-3 Ideal Gases. In this particular section, we are going to show you how all of the gas laws that we talked about in the previous sections are wrapped up in what we call the ideal gas law. And that ideal gas law is written out as PV equals nRT. PV equals nRT. Let me go ahead and get my pen ready here. And when we're talking about PV equals nRT, let's define a few things. First of all, P is obviously the pressure, but we're going to be using units of either kilopascals or atmospheres. All right. Now you can use the other units, but then it's not necessarily you would have to actually use a different gas constant. We'll talk about that in just a second. The volume, V, we are always going to use liters. N is still the number of moles. R is what's called the universal gas constant. And let's rewrite that. There we go. Universal gas constant. And the temperature is T. This is, of course, the absolute temperature. And that will be in Kelvin. And so if you look at these units, when we use a universal gas constant, we're going to be using one of two values. You either have to use 8.31, which would have a unit of liter kilopascals per mole per Kelvin. You're going to be using this if you're using kilopascals as your pressure unit. The other unit the other constant that you could use is 0.08206, and you're going to use that when you're using the pressure unit of atmospheres. The units for this is liter atmospheres per mole per Kelvin. All right. So obviously you would use that particular one when you're using a pressure unit of atmospheres. Now you could make other constants that would fit all the other pressure units, but we're not going to do that. These are the two constants that we are going to want to use. And so let's go ahead and scroll down to example number 1 and show you how this thing works. It says when the temperature of a rigid hollow sphere containing 685 liters of helium gas is held at 621 kelvins. The pressure of the gas is 1.89 times 10 to the third kilopascals. How many moles of helium does the sphere contain? So all you're going to do is start off with PV equals nRT. We'll go ahead and identify what we're looking for. We're looking for the number of moles, so I'll go ahead and color that in red. And so now we're going to go ahead and divide the RT over to the other side. We'll divide both sides by RT. And what you're left with is N equaling PV over RT. And now you simply can plug in your units and solve for N. So the pressure in this case is going to be 1.89 times 10 to the third kilopascals. The volume is going to be 685 liters. The temperature, I'm going to actually switch these. Well, we'll go ahead and put the gas constant in here. R, in this case, because we're in kilopascals, is going to be 8.31. I'm going to put the units elsewhere in just a second. And the temperature is 621 kelvins. Now the reason why I'm going to move the units for this gas constant over is because I want to show you how they can cancel out. Here's the units for the gas constant. It's liter kilopascals over moles in Kelvin. Now notice that I've written the reciprocal of this because we have the 8.31 in the denominator, so that means that we're going to have to also take the reciprocal of the units. And now notice if you cancel out all the units, the liters divide out with liters, the kilopascals divide out with kilopascals, the Kelvin divides out with Kelvin, and the only unit that we're left with is moles. We're looking for moles, and now if you perform the calculation, 1.89 times 10 to the third times 685 divided by 8.31 divided by 621, I'm getting 251 moles of helium gas in that particular sphere. And that's all you need to be able to do with PV equals nRT, at least in this case, is simply realize that we're solving for one variable, rearrange the equation, plug in the numbers, and crank it out. All right. Now, in the next example, we're going to be using PV equals nRT to solve a Boyle's law question. You can actually use PV equals nRT to solve any gas law question. So let's show you how we do this. The question is: a balloon contains 30.0 liters of helium gas at 103 kilopascals. What is the volume of the helium when the balloon rises in altitude, where the pressure is only 25 kilopascals? And we're going to assume we have a constant temperature and the number of moles. Okay, so here's what you do. You have PV equals nRT. Now, what ends up happening is, or another way that we can think of this, is to simply say that we have P1V1 equaling nRT. The pressure times the volume is always going to be equal to nRT. It doesn't matter if we're talking about before the balloon rises or after the balloon rises. So we can still say PV equals nRT after the balloon rises, but we're going to have a new pressure and a new volume. So we're going to call that P2 and V2. Well, here's the deal. If the original pressure times the volume equals nRT, and the final pressure times the volume equals nRT, now remember, the number of moles and the temperature remains constant, so that means this nRT is remaining the same. So therefore, we can substitute in P2V2 for nRT. So what we're left with is P1V1 equaling P2V2. And now we can plug in our values and solve. So our original original pressure is 103 kilopascals. Our original volume is 30 liters. Our final pressure is 25.0 kilopascals. And our final volume is unknown. We don't know what that is, V2. And so now we can simply divide both sides by 25.0 kilopascals. This entire term divides out both the number and the unit. Over here, the kilopascals divide out with kilopascals. We're left with just liters. We're looking for volume in liters. And so therefore, if we take 103 times 30 divided by 25, our final volume is going to be equal to, well, let me go ahead and write this out over here just so you can see it. Kilopascals, 30 liters, 25 kilopascals, and again the kilopascals divide out, and so therefore our final volume is going to be 124 liters. Okay, so that's using PV equals nRT to solve a Boyle's law question. In the next podcast, we're going to show you how PV equals nRT can be used to solve any of the gas law questions. We'll see you next time.